questions. It does. Hooray. Yeah, I think everything's going. Hello, everyone. How's it going? Sweet. My name is Cameron. I'm back today with the second workshop of the Python series for natHACKS. I suppose there's also slides for this, but there's nothing in this. The slides only tell you to go to this, so I'm going to start here anyway. On the Jupyter Notebook, to get to this notebook, you can type in natHACKS.ca /WS1. And I'll leave that on the screen for just a second. And that will load up today's workshop. Today we're going to go through a bit less content than we did last time, but hopefully it'll be a little bit more in depth and a little bit more important information, I suppose. Well, not that the other stuff wasn't important, but you can do the cool stuff now that we're all up to speed. So we're going to be focusing on the Fourier transform, power line removal, and I guess at the end we have like a little exercise to practice some of these stuff. So should hopefully be pretty cool. In this workshop, we're going to cover a little bit of the little bit on libraries, but not a ton. Really, the important bit with the libraries is just kind of like, here's information that you can use. You can, for the most part, even for the hackathon, just like copy and paste what is here, and you can probably get something running. So yeah, without further ado, I suppose we can go ahead and get started. So in this first code block here, I guess, do you have it open? Sweet. So yeah, in this first code block, this is kind of like a bit of a cheeky way to be importing stuff. There is, I suppose, tutorials online for like importing based on your environment and like what kind of computer you have, because there's going to be some differences. But for this case, for the sake of the workshop, we can import the libraries, and what these 4 lines of code here, importing the system and then running a couple executable functions on the system. What this will do is just download the libraries from the internet if Colab sees that you don't have the libraries. And then these lines here are kind of the important part when it comes to the Python programming of it. These are going to make sure that your libraries are accessible throughout the rest of your script. So Shift Enter to run this. It'll complain because Google doesn't trust me, but you should be safe to trust me, I hope. And it will likely run for a little while just because I haven't run this code block in a while. And it'll go through all of my stuff and see if I have it downloaded. And hopefully there's no errors. I guess when you run through this, do you get any, does it give you like the done and like, cool. So using these libraries, I guess I can really quickly go over like the purpose of each of these libraries and just instead of going over it. So matplotlib .pyplot is a library that allows us to like graph out stuff. So if you ever wanted to like look at a graph representation, or like if you've read a research paper, you've probably seen a matplotlib plot. NumPy is essentially the math library of Python. It just kind of does like some of the bigger brain stuff that Python doesn't do. And then SciPy, SciPy, I always pronounce that wrong. It's a library that allows us to do specifically, well, it's kind of like NumPy. It does a lot of the math stuff, but I find that SciPy tends to do a lot more of like the wave and like signal processing stuff that is useful for doing projects in the brain-computer interfacing world. So, all that being said, what we can do is work our way through doing a Fourier transform. Are you familiar with the Fourier transform at all? No. Oh my goodness, I totally should have introduced this. I guess what we can do, hyperlinked here is an interactive site that hopefully still works. Hooray. So I guess this website describes the Fourier transform a heck of a lot better than I do. Essentially, you can take, I guess in this animation here, you can take any image that can be a single line drawing and represent it by a series of circles that can trace it out, which is one sort of application of it. But I guess that example is not super clear where this example intersects with brain-computer interfacing. So if I scroll down a little bit, it'll start, I guess, being a little bit more clear. So when you work with sort of interfacing with the body, and I guess my experience is mostly with electroencephalography, the EEG. If you have like a Muse-S, Muse-2, or like an OpenBCI, you're going to be reading your brain waves, and they're represented just kind of like any old sine wave, or well, any old wave. And what we can do with the Fourier transform is take this wave, any wave, and we can deconstruct it into the pure sine waves that would make it up. So it will give us sort of the range of frequencies and then the strength of each of those frequencies that we can find in that wave. So if we, I guess, yeah, another example, kind of a more extreme example is like with a square wave where it's just, you know, the binary on and off. And it's not immediately intuitive how you'd model like an on and off wave with a sine wave, but if you have infinitely many of them, you can, with adding layers of like, refine it down so that it models this wave exactly. And yeah, you need a lot of them for it to look really good. So I guess the animation there, like it looks pretty good when you, yeah, anyway, I hope that's somewhat sensible. I like this website because you can like kind of draw your own thing and it'll like do the transform and show you the waves that you want. It's pretty nifty, I think. Beyond that, where this becomes useful in our application of brain-computer interfacing is by being able to deconstruct the wave. We can apply different practices or different like patterns used in neuroscience. So you may be familiar with like alpha waves or beta waves, like different frequencies within the brain. Essentially what those are is just different collections of brain frequencies. And the way you can get these collections is by taking the raw brainwave and passing it through the Fourier transform. Yeah, that's fine. I decided to set up the computer for the recording and streaming over there today because that's how we can get it on the projector. Oh yeah, we have a projector today. That's the way we can get it on the projector, but it's kind of hard to read chat from over here. Sorry about that. Cool. I guess we can go through. I guess, do you have any questions about the rambling description I gave? Cool. So how does all of this look in code? Well, what we can do is kind of create a mock scenario and generate some waves for us to work with. So we can define a variable called time and just input kind of like array of values into it. So what NP linspace does, actually I should just add a little example here. Excuse me. So if I have a code block and I create the variable time, I can just print out time and show what's going on under the hood here. So what this is saying is I want to go from the number 0 to the number 0.5, and I want to have 500 steps in between it. So if I were to create maybe a more human-readable version of this. This would say I want to go from 0 to 20, and I want there to be 10 steps. So this will give us back a list of, have I done this wrong? What have I done? Yeah, I'm confused by this again. I think I always confuse linspace, and there's another one, arrange. This is what I get for going off script. Live debugging. Yeah, I suppose, anyway, what this does is it just generates a list of evenly spaced values somehow. What we can do with that list of evenly spaced values is we'll use it to generate a sine wave. So this is just a variable, I guess. Do we even use this again? I think we use it much later, but we generate our time, and then we can define 2 sine waves. So the only 2 parameters really that you, like the minimal 2 parameters you need to define a sine wave are going to be the amplitude of it, so how tall it is, and the frequency, and or the wavelength, just kind of how long the waves are. So here we'll just generate 2 waves with the amplitude of 1.5 and frequency of 10 and 35 hertz, which should be pretty similar to like waves that you would see when you're doing like EEG analysis. With EEG, I guess I'm pretty sure we'll be opening up some files later on, but with an EEG recording, you'll have usually the majority of your frequency around the 5 to 12 hertz area. And more broadly, like 0 to 30 is kind of like where most of the meat is. So these should be somewhat representative of waves that you would see. And what we can do is use numpy, which we've aliased as np. I should have mentioned that there. We can use numpy to generate some sine waves. So if we run this code block finally, it will create the 2. It'll print out sine 1, sine 2, and we're using matplotlib here just to generate these plots. So the first one, the 10 hertz wave, amplitude of 1, and 10 hertz. So over the period of a second, it should oscillate 10 times. So over half a second, it oscillates 5 times. Hey, that checks out. And then this guy's 35 hertz and 0.5 amplitude. And the, I guess what we're going to be doing, kind of like specifically why we've generated these 2, is because we can combine them, and that gives us a more complex wave. And we're going to give ourselves the challenge of taking that kind of gross looking wave and figuring out what frequencies make it up. So what we can do is pass in, I guess we'll use numpy again. Theoretically, you can go through and do all of the brute force calculations to say, like, this is like how you would go about doing a Fourier transform. It's pretty involved though, and I'll be honest, I've never actually gone through the math and done it all myself. You don't really need to. You can just use a library to achieve that. So we can take this complicated wave and we'll pass it into a function called np.fft.fft, and we'll save this, and that'll grab the y values of the Fourier transformed information for us. And then also what we can do is pass the length of the combined array into np.fft.fft frequency, or FERQ, and multiply it by the sample rate of our headset, So you'll be able to find this online for your specific headset. I think this number was just kind of made up. But we're assuming that the headset that we have samples at 1,000 hertz or 1,000 times a second. So over half a second, we should see that many data points. Or over 1 second, we should see 1,000 data points. Anyway, with that information, we can sort of do the entire Fourier computation. I mean, that's mostly it. Is just kind of these two lines of magic. But of course, we want to actually look at it and see what's useful. So we can plot out kind of exactly what we have. The x value here is the frequencies that we have, so this second bit. And the y value is slightly more complicated. So the Fourier transform operates on complex numbers, and I don't totally understand why, I'll be honest, but the one thing that I do know is if you want to be interpreting the data, at least any time that I've gone to interpret the data, it makes sense to interpret it as a real number. So what you can do to sort of cast that imaginary number back to the space of reals is just take the, I don't actually remember what this is called, but you square the real value, you square the imaginary value, and you add them together. And all of that will give you a graph that looks kind of like this. And it's not super useful looking at this because like all of your information is kind of jammed into this tiny little bit here. So we can restrict the scope of our x values to kind of make it easier to look at that. So from the last workshop, we talked a tiny little bit about slicing. So you can use array slicing to get rid of some of this information. So one thing with the Fourier transform is it's going to give you an exact mirror of your information about 0. So really, we don't care about anything that's going on in the negative frequencies. I mean, kind of, but like, we can just pay attention to the positive frequencies and get the exact same information. So what this does is cuts that off. So if we run that, it just shows us from 0 hertz to 500 hertz. And then similarly, oh, hello. Similarly, we don't really concern ourselves in brain-computer interfacing. The brain can produce oscillations above 100 hertz, but it's not super common. So likewise, we can trim off everything above 100 hertz, and then we can see a little bit of our information. So just looking at this visually, we have 2 main peaks that come from our data. We have one peak around 10 hertz, and we have one peak around 35 hertz. And the 10 hertz peak is a heck of a lot bigger than the 35 hertz peak. And if we, cheat a little bit, we can see the waves that we put into it. 10 hertz and 35 hertz, hooray, that worked. And the 10 hertz one was twice the amplitude. So the output that you get is not going to be linear. So even though the amplitude of the 10 hertz one was twice that of the 35 hertz one, they aren't necessarily 2 times the size. But usually when we're working with these applications, we don't concern ourselves too much with the raw values. What makes these numbers and this information important is how it compares to other pieces of this information. So the unit and the scale doesn't matter too much. Let's see if we have. Yeah, we didn't actually, or we won't be covering that in this, so I'll go on a quick ramble. One thing you can do, I would recommend looking this up if you do have like some extra time between now and natHACKS. It's a decently fun exercise to kind of get warmed up to the idea of like processing brain signals. What you can do is one of the most clear things that you can sense with brain data is if a participant has like their eyes open or closed in a reading. And the way that you can determine that is based on how how this plot changes based on, or how a plot of two different recordings compares. Typically, if your eyes are open, there's going to be a lot more there's going to be a lot more low frequencies. And if your eyes are, if your eyes are open, there's going to be more high frequencies, and if your eyes are closed, there's going to be more low frequencies. Specifically, you can look at your alpha and beta bands. I don't think I have those laid out here, but there I go again, going off script. So yeah, I have a little activity here. This is kind of the same thing, but without all of this like text in between. So like you can run all of the code that was above just in one little bit. What's kind of fun about this is you can go through and like give whatever amplitude and frequency and kind of see how that responds in the frequency domain here. So if we maybe plot out like 5 and 75, they're roughly the same amplitude or magnitude, and yeah, 575. So in this case, we're taking some information, encoding it in some secret way, and then we're using an imperfect way to decode it. But typically, you just won't know what these are. So with your brain recording, you can just feed that in there, and then it'll give you that information back. So this is kind of a silly example, but I guess illustrates the point. I guess that's a decent place to pause. Did you have any questions? Sweet. So, yeah, actually, it looks like I did. So, back when I was, I guess, going like a minute ago, when I was talking about the alpha, beta, theta brainwaves and the different bins, that's what we're going to talk about now. Crazy, that's a great time to bring that up in the Google Colab here. So, for power band binning, essentially what we do is we take this graph and we just kind of draw lines. They're somewhat arbitrary. Researchers have kind of agreed like these are where these bin lines should be, or this is where it's most effective to put them. So I'm a computer scientist. I'm going to trust that those are the right numbers, and that's kind of how we go. I know that there is a decent amount of debate around like if what exactly they should be, and different programs will use different values for these, but for the most part, they're kind of in similar places. So as long as you're kind of close to those cutoffs, then you should be seeing similar results. So I have some data here. This was recorded using a 16-channel OpenBCI headset. And for the sake of simplicity, what we're going to do is just get rid of 15 of those channels and pay attention to one. So if you click on the link, it will complain that you're leaving Colab. And they have a cute dog too. I didn't know that was there. And you have some files. So you can go ahead and download this. And then in Colab, the way that we can get these files in here is just going to the sidebar, clicking on this file guy here, and clicking this button. No, that's the wrong one. I usually do this a different way. You can upload files with that, and let's go ahead and unzip this really quickly. So you can upload these files, and it'll give you a reminder, these files aren't going to be saved here. It's not quite like Google Drive, so just make sure, if you do want to use this example later, that the CSVs stay on your computer. I suppose can quickly open up and show what the data from an OpenBCI headset looks like. It can look a couple different ways, but at least this way is there we go. This is the most naive way, I guess, I could think of storing the information. So what we have is essentially just a big old table. On the columns here, these are just each of the individual channels. So these are the different electrodes placed around your head. So this column here would just be like one specific area, like right here, for example. And the values going through are just, I believe the OpenBCI is 256 hertz. I'm not 100% sure on that, and I know that you can change it in software. So this recording at least was, I think, 256. So each of these is 1/256th of a second, and this is the this is the voltage. Yeah. Hello. This is the voltage in some unit at that point in time. And yeah, if you were to plot this out, it would give you, I believe we will actually plot it out. So instead of describing it, we can just go ahead and go through. So that's how it looks as numbers. But what we can do is open the data, format it a little bit so that we can kind of like ignore the 15 channels that we're not going to care about for now. And then we'll plot it out. So I believe this is, in past workshops when I've given this, I've like gone through and like typed all this out. So like, I never quite trust. Yeah. So, right, it's expecting it to be in data. Today we didn't upload the data file, so if we open with powerline.csv, it should still complain. No such file or directory. Okay, / with powerline.csv. So you can open it using this syntax. So with open, and then the R here just means that we're reading the file. So we're going to kind of prevent ourselves from overwriting any information in the file that, we're just going to prevent ourselves from writing to it so we can maintain the integrity of the data. And we're just naming this variable, this file object data. Then what we can do is iterate through all of the data using our for loop. So this will just take line by line. So you can imagine each of these is one line. So our for loop is just going to step through and do all of these. And for each of the lines, they're separated by commas. So my spreadsheet program was kind of smart. Everywhere that it saw a comma, it just kind of said, oh, I'm going to make that in the next column. But here we're just going to take the commas and say, okay, we'll split this out into a list. And then we're only going to record the first value of it. And we're going to do a typecast to a floating point number, just because the file, it's reading it as a string, and we don't want to interpret them as strings. So we have our floating point number. And then finally, we just use the array append to add it to the channel here. So if we run this, it's already been run. It doesn't have any output, but we can give it output. So if we add a new line, we can say something like print channel. And it's just one big long list of a bunch of values. And conveniently, these values, 265, are exactly that of this first column here. So essentially what we've done is just taken all of this and said, delete columns. Is it going to let me do that? No. Okay, never mind. We've deleted all, we only have the first column. What we can do is plot it. So it's just using NumPy. And this is kind of what the brainwave looks like over that 1 second sample. Now, when this sample was recorded, our headset was set up improperly. So I honestly don't really know what the problem was, but for some reason let's see if we can zoom in here. So if we said maybe 50, and we plotted out fifth channel from 0 to 50. Yeah, so what it seemed to be doing was kind of like taking, if we had an average point, every other sample was just the negative of the last one, which is not, it's not expected that your brainwave would look like that. So what we can do in this case was to kind of sacrifice a little bit of our sample quality and just throw away half of our samples. So every other sample was negative. So if we just delete every other sample, then we should only have the positive half of the curve. So if we, it's essentially what this piece of code is doing. It just kind of goes through and says if the index that we're on is odd, then just copy over the last sample that we have. So we still have the same sort of 250 samples, but we only have really half the resolution. Can plot this out, and then we'll see we have a slightly more realistic looking brainwave that has the more characteristic kind of like, stacked sine waves sort of look to it. In this case, it's really obvious where there's this really high frequency one and there's the lower frequency. And then there's even a lower frequency sort of under all of it. You can kind of see there's the wave trend there. But yeah. So now that we've opened up this information, we can just use the exact same trick that we did earlier with the fake synthetic data. The only difference is here, instead of saying that the data is 1,000 hertz, we're going to say it's 250 because we recorded it at 250. And then, yeah, we remove the unnecessary negative reflection because we don't care about the negative part. And we can cast the Fourier transform to the reals and just plot out what we see. And this is usually what you'll see with a brain recording. Usually you'll have most of your peaks kind of like under 20, and then kind of an exponential kind of fall off up into 100. Sometimes you'll see stuff at 120, I suppose. It is likely, one thing that stands out here, I guess, is, you have the big spike. We kind of expect to see spikes here, and it falls off and goes down to almost nothing. But we do have, I guess, two big spikes here, and then also kind of a spike at 120. We don't really expect to see much brain activity there, and especially with our big spike here right at 60. That is a sign of a problem, and thankfully it's a pretty easy to fix problem, and I believe that's what we'll be going into shortly. Not right away though, but that's kind of what a frequency domain for a real brain recording looks like. That's essentially what I said there too. So plotting. What we can do is pretty much the whole binning piece. We'll just draw these arbitrary lines at the different points and take the average value of all of the points in each bin and just plot that out. So this defines a function that just plots out a list of 5 values. This is just kind of a piece of convenience. Just kind of looks pretty. And then what we can do is, I suppose, go through the frequency plot and just figure out our average values and plot those out. So what this does is it just goes through for each point, and if the point is sort of within the 4 to 8 frequency range, so, if it's less than 4, we're going to consider it to be a delta wave, because delta, at least in the definition that I looked up, is 0.5 to 4 hertz. And then here, theta is going to be 4 hertz to 8 hertz. So if it's not delta, then it has to be something higher. And then we can use our elif, and we can kind of assume that it's greater than 4 because it already made it past the if. And essentially add the value of that point and a count just so that we can average it out pretty easy. And then right at the end, Python gives us a nice sort of ease of use convenience stuff for computing like entire values of arrays. So this is kind of gross shorthand, but we take the value of the total of each and we divide it by the count of each and cast that back to a list. And what that'll do is give us a list of 5 values, all that represent sort of the average magnitude in that area. And then what we can do is take that function we defined earlier and just plot them out. So it does follow pretty much the trend of the overall thing, but with these it's a little bit easier to look at kind of like how these different bins change over time, and with these it's a little bit easier to kind of compare one-to-one. And then also you can reference different neuroscience research papers and use some really more grounded scientific methods to validate your code. So that's on plotting. I think a lot of this too, at least for this workshop, if you do like run into problems during the hackathon and like you want to like see what your wave looks like, I think this is a good place. I come back here pretty often whenever I'm working on like BCI stuff to just copy and paste like, oh, can I plot out what I'm looking at just so that I can understand these numbers a little bit more? Yeah. So this is a good time to pause. Any questions? Cool. So a little bit of practice. Using our FFT and pre-processing kind of knowledge, we can do what I'd like to, I think this is probably the easiest filter, or the easiest example of a filter. So we can remove the power line. So going back to this plot out here, there was that big spike right at 60 hertz. It's when you see something, especially at exactly 60, going back to, I believe this was actually mentioned in the workshop yesterday as well, in the intro to neuroscience. If you see the spike right at 60, it's likely that that is not representative of brain activity. Within North America and the majority of the world, I think it's just like Europe and Japan that have the 50 hertz system, but the AC system, everyone is kind of agreed that it should be running at 60 hertz. And the electrodes that we have to sense this brain information, like our brain is not super loud about all of the like energy that it's moving around inside of it. So we need to have really sensitive electrodes, electricity sensors to be able to pick that up. And the electricity sensing is sensitive enough that it will actually pick up oscillations of like power lines in the walls. So you're likely to see something like this. And that can, like in our example here, kind of perturb the data. So our alpha is probably quite a bit higher than it should be. But we wouldn't really know that unless we looked at the full graph and saw that spike at specifically 60. So it's a pretty easy problem to fix. Essentially what we'll do, I'm just gonna re-import the thing. It's gonna complain because we don't have a file named data, but that's all right. We just get rid of it. Yeah, so we import that and apply the Fourier transform. So here I actually did get rid of it, so we'll have to scroll back and forth a little bit. So to get the data, these are going to be the y values. Comes from, I'll just copy all of this. going to look something like that. And here we've creatively called it channel data instead of channel. So this will define our y values, this will define our x values, and I can get rid of this because we're not going to use that anymore. And then also we can plot out the transformed data. This part just removes, or this is here to remove the negative and the part that we don't care about. So I can scroll back and just steal that from here too. And I'll just change the names of these variables too, because we're referencing different things. And these ones as well. And that's a really funny looking chart. What did I do wrong? Magnitude, frequency. Why are they in that order? Okay. So this should be here. This should be here. There we go. So I guess the problem I ran into there, I just copied and pasted in the wrong order. I put these in a different order. You know, I wouldn't be surprised if, like, when I was doing this, I did that on purpose so that it was like a puzzle to solve. Anyway, so here's the plot. It's the exact same thing that we had before for the most part, but now we can reference it differently and get rid of this 60 hertz. And the way we can get rid of it is really simple. Here, like, this is honestly even kind of overkill, defining the variables of it, but the main idea for the problem solution is we're just going to say, here's these frequencies from probably 60 hertz plus minus 1, and instead of them being a magnitude of like 1, we're going to say that they're a magnitude of 0, and then that spike will be gone. There is smarter ways to get rid of the power line interference, where like you can try and estimate what that brain information would have been, but for the most part, brain information there is gone. But that's kind of okay because our brain happens to oscillate at a different frequency than the power line most of the time. So anyway, we can set our cut frequency to be 60 hertz, and here I've just called it tolerance, but that's just kind of like the plus minus around it that we want. I'll just set it to 2, I think is a good amount. And then the way we kind of achieve this is just with array slicing again. So here we have the FFT data, the y values, and we're just going to say from the start point, so we'll say cut frequency, minus tolerance, put the colon there to say that we're slicing. So the first index is 60 minus 2, 58, and the second index, the end point, is going to be our cutoff frequency plus the tolerance, so 62. And all we're going to do with however many values happen to fall in between there, we're just going to set them as 0. And this is the same code as above, then why wouldn't you put it there? Why did I make it like this? Plot our result. This is the same code as well. Frequency. Right. So I think it's this part. And of course, it's in a different order. Okay. There we go. So we still kind of have that spike there, but that one isn't right on 60 hertz, so that might be brain information. But it did get rid of that piece of interference. One thing to note as well, kind of not necessarily a quirk of the Fourier transform itself, but just kind of by the nature of like how these waves are working. At your resonant frequencies, you will see sort of smaller effects of changing these things. So 120 is exactly double of 60. So when we reduce the spike at 60, we also cut down on that spike at 120. It's likely that what the Fourier transform is sort of getting here, that information, it's just kind of seeing a 60 hertz wave and misinterpreting it a little bit. It's a really hand-wavy way to describe that. If anyone who studies math heard me, thank you. That would definitely frustrate them. Hello. Perfect. I think the hardware workshop's going to be starting in about 30 minutes. So we're just going through a little bit of Python and Fourier transforms and stuff today. So yeah. Another cool thing you can do is kind of like apply the inverse Fourier transform. So, I'm just going back into the workshop. Yeah. Another thing you can do is apply the inverse Fourier transform to sort of this result, and it is, I mean, it's so much less complicated than it sounds. These three big complicated words. Essentially, what we're doing is just taking all of these different frequencies and putting them back together into that wave. So, like right at the start of the workshop, when we sort of defined these two and then added them together, it's kind of what we're doing with the inverse Fourier transform. We have our two, or like we have sort of this, I mean, it's computer, so it's not infinite, but this theoretically infinitely long list of different sine waves, and we're just summing up the values again. So essentially what that does is it just takes us from this Fourier, or this frequency domain back into the time domain, which just shows a normal looking wave. And okay, yeah, we do actually use it. So we can check our answer. When we downloaded the files, we downloaded two, one called with powerline and one without powerline. In this case, when I was recording, I couldn't actually, like, the headset was filtering out the powerline information itself. Sometimes it does that, sometimes it doesn't. When I recorded this, it did, so I added my own powerline. So we can compare our results of the wave before and after removing it. So this is the one that we figured out. We added we added the powerline interference and we removed it ourselves. And we have the plot of what the brain data actually looked like. And they're a little bit different, but they carry pretty similar information. So given that we've added what would be a lot of noise and taken it back out, we have pretty much the same, or well, similar enough signal. I think that's about it, all that there was for this workshop. Yeah. I guess any questions on any parts of that? Cool. I'm going to open up the live stream on my phone and see if anyone had sent a chat message through any of that. Yes, I can put the notebook link in the description. I hope that wasn't asked a really long time ago. It is NeurAlberta. No, that's a different website. natHACKS.ca/US1. That one's not quite the description, but it does work. I can also just type it out here. So awesome. So yeah, I guess thank you for your attention. Thank you for hanging out. I hope. Sweet. Yeah, I think the next one is, yeah, I think it starts at 5:30? I'll double check before, sorry.
That's okay, I should probably check.
Yeah, 5:30, so, yeah. All right, see you soon. Yeah, I guess for the live stream, I'll go ahead and close it out. If you do have any questions, you can reach me on the Discord. You can probably find me by just searching for Cameron. Yeah, thank you for hanging out, checking out this stuff. Yeah, I think one of the biggest takeaways from this workshop wasn't necessarily, well, hopefully was a little bit of the knowledge, but I think at least for the purposes of the hackathon, there is some useful bits of code here to kind of nab out and solve some sort of like, oh, I need to work through this pipeline. So decent place to copy and paste some template code. Yeah, thank you for joining me for today's workshop. I put the mouse over here.